September 9, 1940, Inglewood, California, 11:47 a.m. Inside the North American Aviation factory, Chief Engineer Edgar Schmood stood next to a polished silver aircraft that, by all rights, shouldn't have existed yet. Just 102 days earlier, this machine had been nothing more than rough pencil lines on a draftsman's paper. Now it was real, fully assembled, and about to challenge everything engineers thought they knew about aircraft cooling. Under the fuselage, a strange-looking bulge caught the late morning light. It wasn't a bomb. It wasn't an external fuel tank. It was a radiator scoop, one that would go on to rewrite parts of aerodynamics. Here's what nobody expected. This cooling system wasn't only going to dump excess heat. Under the right conditions, it would actually turn that heat into forward thrust, converting what had always been an aerodynamic handicap into a potential advantage. German engineers dismissed the idea as fantasy. Many British designers stayed doubtful. Even in the United States, aircraft engineers struggled to fully describe what was happening. But the math worked, and later, so would the combat record. This is the story of how British physicist Frederick William Meredith's radical 1935 theory ended up becoming the P-51 Mustang's hidden ace. A physical effect so unintuitive that even 8 decades later, engineers still argue over whether it truly generated thrust or merely erased cooling drag. What we're about to examine isn't just the tale of a single airplane. It's the solution to an engineering problem that had plagued every liquid-cooled aircraft since World War I. To see why the P-51's radiator was so revolutionary, we have to go back to the mid-1930s, when aircraft were finally breaking the 300-mile-per-hour barrier. Designers were cornered by a brutal trade-off. Liquid-cooled engines allowed sleek, low-drag cowlings and superior performance at high altitude compared to air-cooled radial engines. But they came with a catch: radiators. These radiators were big lumps of metal and fins sitting directly in the airstream, piling on drag. At the Royal Aircraft Establishment in Farnborough, England, a 35-year-old engineer named Frederick William Meredith became fixated on this challenge. While most of his colleagues focused on clever ways to reduce radiator drag just by repositioning and shaping it, Meredith posed a different question. What if you could use the waste heat itself? On August 14, 1935, he published his landmark paper, Cooling of Aircraft Engines with Special Reference to Ethylene Glycol Radiators and the Effect of Ducting. The title sounded dry. The consequences were anything but. Meredith's insight was beautifully simple. Every piston engine throws away an enormous amount of energy as heat. That heat must be dumped into the atmosphere. Traditionally, that was pure loss, energy spent for no gain, plus the drag cost of the cooling system itself. Meredith realized something remarkable. If you carefully design the airflow passage around the radiator, that waste heat could actually increase the speed of the air leaving the duct. As the air heated up, it expanded. If that expanding air was guided through a converging nozzle, the expansion would accelerate the flow. Faster flow meant more momentum. More momentum meant thrust. This wasn't some perpetual motion fantasy or magical free energy. It was straightforward thermodynamics, specifically an open Brayton-like cycle: compression at the duct inlet, heat addition at the radiator core, and expansion through the outlet nozzle. 3 basic steps, which if executed correctly, could cancel out or even completely overcome the drag of the cooling system. The theory was solid, the equations held, One major issue remained. No one had yet built a real-world system that delivered the dramatic performance Meredith's calculations suggested. British designers moved quickly to apply his ideas. The results were uneven. The Supermarine Spitfire flew for the first time on March 5, 1936, just 7 months after Meredith's paper, with a ducted radiator beneath its wing. The Hawker Hurricane followed suit. Both aircraft used the new Rolls-Royce Merlin engine with ethylene glycol coolant, the exact setup Meredith had analyzed. But in practice, neither aircraft achieved the dramatic drag reductions his equations implied. The German Messerschmitt Bf-109 originally used a single underslung radiator, then switched to wing-mounted radiators in 1938. These turned out to be even less efficient, plagued by severe inlet separation and chaotic airflow that degraded cooling performance and added drag. So what went wrong? 3 major issues crippled these early attempts. First, duct geometry. Most designs used very short passages between the inlet and the radiator face. On the Spitfire and Bf-109, duct lengths were measured in inches, not feet. Air had to turn sharply, sometimes 30 or 40 degrees, which caused it to separate from the duct walls and become turbulent. That turbulence meant poor pressure recovery, inefficient heat transfer, and more drag instead of less. Second, boundary layer contamination. As aircraft fly, a thin layer of slow, disturbed air clings to their surfaces, the boundary layer. This sluggish, turbulent air is terrible for radiator performance. Early designs allowed this boundary layer air to flow straight into the radiator inlets, cutting efficiency by 15 to 20%.
Third, exit geometry. Meredith's concept only worked if the heated air was released through a properly shaped converging nozzle. Most aircraft of the era used crude flaps or simple doors with almost no aerodynamic refinement. Without a true nozzle, the hot, expanding air just spilled out in chaotic turbulence instead of generating meaningful thrust. The Bf-109G suffered so severely from these combined issues that cooling drag accounted for an astonishing 14% of its total drag. Opening the radiator flaps at high power settings could chop as much as 30 miles per hour off its top speed. Even aircraft that were considered successful, like the Spitfire, never achieved genuine Meredith Effect thrust. They reduced cooling drag primarily through variable exit doors that restricted airflow during cruising, but the deeper physics Meredith had described remained out of reach. By 1940, more and more engineers were starting to suspect that the Meredith effect might be more theoretical curiosity than practical engineering tool. That skepticism persisted right up until North American Aviation received an unusual and urgent request from the British Purchasing Commission. April 1940, Los Angeles. The British Purchasing Commission approached North American Aviation with a demanding proposition: design and build an entirely new fighter to supplement Curtiss P-40 production. The deadline was brutal. First delivery required by January 1941. That meant the engineering team at NAA had just 120 days to go from concept to a flying prototype. Most aircraft manufacturers would have turned the request down immediately. But NAA President James Dutch Kindleberger saw an opportunity too big to ignore. Heading the design effort was Edgar Schmood, the 41-year-old Austrian-born engineer whose obsession with aerodynamic refinement bordered on the extreme. His background was unusual. He'd worked for Fokker in Europe and for General Aviation in the United States before joining North American. Few people understood both European design thinking and American production methods as thoroughly as he did. The British specifications were sharp and uncompromising. A fighter powered by the Allison V1710 engine optimized for high-speed, low-altitude performance. Range and level speed were far more important than climb rate. Schmood made two groundbreaking choices that shaped the NA-73X prototype, the aircraft that would later become the Mustang. The first was adopting the NAA-66 series laminar flow wing. This new airfoil design maintained smooth, low-drag airflow over a much longer portion of the chord than conventional wings. The resulting drag reduction meant the aircraft could tolerate slightly higher cooling drag and still remain fast, an essential consideration for what Schmood had planned next. The second decision was the installation of a ventral radiator scoop positioned behind the wing's trailing edge. This was where Meredith's theory would face its first real chance at full-scale validation. Schmood examined the cooling problems that plagued European fighters. He reviewed every piece of wind tunnel data he could get, including test results from the Curtiss XP-46 program. NAA even paid Curtiss $56,000 for that technical information. The XP-46 had experimented with aft-mounted radiator scoops, but Curtiss never developed the idea thoroughly. Schmood took the concept dramatically further. The Mustang's radiator installation incorporated several innovations that earlier aircraft had missed entirely. First was the long diffuser duct between the inlet and the radiator face. Running nearly 30 inches, triple the length found on the Spitfire, this duct allowed the incoming air to slow and compress smoothly without stalling. The diffuser walls never exceeded a 7-degree divergence angle, keeping the airflow fully attached throughout the passage. Next was boundary layer control. The inlet included a precisely engineered scupper, a small auxiliary opening that siphoned off the slow, turbulent boundary layer air clinging to the fuselage surface. Only clean, high-energy air reached the radiator core. This single improvement boosted cooling efficiency by roughly 15%. Then came the convergent exit nozzle. The downstream end of the scoop narrowed into a true nozzle shape, and variable exit doors allowed the pilot to fine-tune the throat area. With the doors mostly closed during cruise, the system produced maximum velocity acceleration. Opening them during climb or ground operations provided increased cooling when performance mattered less. Finally, Schmood integrated 3 heat exchangers into a single airflow pathway: the coolant radiator, the engine oil cooler, and the supercharger intercooler. All 3 benefited from the highly controlled airflow architecture. The NA-73X prototype was finished on September 9, 1940, exactly 102 days after the contract was signed. Test pilot Vance Breeze took it into the air on October 26. Early trials exposed issues. The scoop produced an audible rumble at certain speeds, indicating inlet separation. NAA engineers responded by mounting the actual airframe minus its outer wings inside a full-scale wind tunnel. Testing revealed that separation occurred where the duct diverged too abruptly. The solution was to reshape the inlet and refine the boundary layer scupper even further. By the time the P-51B was introduced in 1943, now powered by the Packard-built Merlin 1650 instead of the original Allison, the radiator system had evolved through hundreds of test flights into one of the most aerodynamically efficient cooling installations ever built. But did the Mustang's radiator actually generate thrust, or did it simply neutralize its own drag? To answer that, we need to look at 3 essential performance metrics: pressure recovery, temperature rise, and exit velocity. Pressure recovery. As ram air enters the scoop at high speed, it slows and compresses, turning kinetic energy into pressure. An efficient diffuser can recover 80 to 85% of the incoming dynamic pressure. The Mustang system achieved an outstanding 84% pressure recovery with the exit door closed, minimizing energy losses before the air even reached the radiator. Temperature delta. The greater the difference between the coolant temperature and the inlet air temperature, the more heat energy transfers into the airflow.
The Merlin engine's ethylene glycol coolant operated at 212 degrees Fahrenheit or 100 degrees Celsius. At altitude on a standard day, incoming air could be as cold as 35 degrees Fahrenheit. That 177-degree temperature difference meant a tremendous amount of heat was being transferred into the airflow. Modern testing by experimental aircraft builders who have recreated the P-51's Radiator setup has recorded temperature increases of more than 120 degrees Fahrenheit during typical cruise. At those levels of heating, the expansion of the air becomes substantial. Exit velocity is the key variable. If the air leaving the duct is moving faster than the aircraft's true airspeed, the radiator system generates net thrust. If the exit velocity simply matches the aircraft's speed, cooling drag is effectively zero. Anything below that threshold still produces drag, but noticeably less than conventional cooling systems. Flight test data from P-51B and P-51D models indicates that under cruise conditions between 15,000 and 25,000 feet at 350 to 400 miles per hour, the system consistently matched the aircraft's forward velocity at the outlet. Internal NAA documents show that at the Mustang's top speed, cooling drag was essentially eliminated. At 437 miles per hour, the P-51D's maximum level speed, the radiator system added no meaningful drag and no noticeable thrust. This was extraordinary. Comparable fighters like the Spitfire and Bf-109 suffered cooling drag equal to 8 to 14% of their total drag at maximum speed, while the Mustang brought that penalty down to virtually nothing. But modern tests have uncovered something even more intriguing. Home builders constructing P-51-style scoops using contemporary thin-core aluminum radiators, much more efficient than 1940s components, have measured exit velocities several percent higher than the aircraft's own airspeed under certain conditions. With coolant temperatures around 180 degrees Fahrenheit and temperature deltas near 125 degrees Fahrenheit at about 150 miles per hour, the outgoing air actually moved faster than the plane itself. This strongly suggests that the wartime Mustang, with its thicker, more restrictive 1940s radiator cores, likely achieved close to zero net drag rather than true positive thrust. The internal flow resistance of the radiator matrix probably consumed any potential surplus momentum. However, highly modified P-51s built for air racing tell a different story. Aircraft like Voodoo and Strega use elongated, shallow scoops, ultra-thin radiators, refined inlet shapes without boundary layer scuppers, unnecessary at racing speeds, and meticulously sculpted exit nozzles. These racers almost certainly generate actual forward thrust from their cooling systems during high-speed runs. The effect on wartime performance was dramatic. The P-51B entered combat over Europe in December 1943 with the 354th Fighter Group, and its blend of speed, range, and high-altitude ability immediately reshaped the bomber escort campaign. With the Packard V1650-7 Merlin producing 1,695 horsepower, the Mustang could reach 437 miles per hour at 25,000 feet. Its combat radius reached roughly 750 miles with drop tanks, enough to escort B-17s and B-24s all the way to Berlin and back. The P-51D, with a bubble canopy and 6.50 caliber machine guns, became the definitive long-range escort fighter of the war. More than 15,000 Mustangs were built between 1940 and 1945. The radiator installation alone contributed an estimated 15 to 20 miles per hour to the aircraft's top speed compared with what the Mustang would have achieved using a conventional cooling layout. In aerial combat, a 15-mile-per-hour advantage can mean the difference between running down an enemy fighter or watching it disappear into the distance. The validation of Meredith's concept influenced far more than a single airplane. It shaped ramjet research. Meredith's thermodynamic cycle, ram compression, heat addition, expansion through a nozzle, directly mirrors the fundamental ramjet process. Engineers noticed the connection almost immediately.
By the late 1940s, American researchers were explicitly investigating Meredith ramjets as possible auxiliary propulsion systems. Although practical ramjet development eventually followed different design paths, the underlying physics Meredith described remained accurate. Post-war designers tried to refine the concept as well. The British Napier-Heston T-5 racing aircraft, conceived between 1938 and 1940, incorporated an even more ambitious interpretation of the idea, channeling its exit duct along almost the entire fuselage length for optimal expansion. The T-5 crashed during testing before the system could be validated, but the design represented the theoretical optimum. The Meredith Effect also became part of the DNA of unlimited-class air racers. Modern, highly modified P-51s, pushing speeds near 500 miles per hour, rely on cooling systems far beyond what was possible in the 1940s, and their radiator installations contribute measurable forward thrust. Even Formula One has adopted the principle. Since the 1980s, F1 engineers have placed radiators inside aerodynamically sculpted side pods that function as Meredith ducts. The hot exhaust air accelerates through converging outlets at the rear, reducing the aerodynamic cost of cooling. Yet misunderstandings persist. Many aviation enthusiasts still claim the Mustang's radiator produced 250 to 400 pounds of thrust, numbers unsupported by wartime data or physics. These myths survive mainly because zero cooling drag sounds less dramatic than free thrust. But the reality is impressive enough. North American Aviation accomplished what many believed couldn't be done, making the cooling system virtually disappear aerodynamically. Why this still matters today is simple. The engineering principles that made the Mustang's radiators so effective continue to influence modern aerospace and vehicle cooling design.
Battery packs in electric vehicles generate large amounts of heat that must be removed efficiently. Companies like Tesla now use cooling ducts inspired by Meredith's principles, designs that take advantage of the car's motion to improve heat dissipation while keeping aerodynamic drag to a minimum. The underlying physics haven't changed, only the way engineers apply them has evolved. Hypersonic aircraft traveling at speeds above Mach 5 face extreme thermal challenges, and researchers in that field study Meredith-style cooling as a way to transform waste heat into something useful, instead of treating it purely as a problem. Unmanned aircraft also benefit from these ideas. Long-endurance drones powered by internal combustion engines encounter the same cooling versus drag compromises that P-51 engineers solved more than 80 years ago. Modern UAV designers openly reference Meredith Effect fundamentals when fine-tuning their cooling systems. The broader lesson goes far beyond airplanes. Waste energy streams can become valuable assets when approached with the right engineering mindset. Edgar Schmood and his team at North American Aviation didn't merely revisit Frederick Meredith's 1935 paper, they executed the theory with a level of precision earlier designers never achieved. Long diffusers, boundary layer control, convergent nozzles, variable exit doors, every piece of the system mattered. The P-51 Mustang earned its legendary reputation because various innovations worked together seamlessly. The laminar flow wing, the Packard-built Merlin engine, exceptional structural efficiency, and of course, the distinctive ventral scoop that transformed a theoretical concept into a wartime advantage. Cooling drag didn't vanish through luck or aerodynamic illusions. It vanished because engineers finally learned how to contour airflow, control pressure changes, and apply thermodynamic laws that had existed long before powered flight. Meredith laid out the mathematics in 1935. Schmood produced the working design in 1940. Combat over Europe in 1944 confirmed both men were right. The Mustang's radiator remains a testament to the idea that even the toughest physics problems often hide elegant solutions, provided someone is willing to question assumptions and execute with precision. If this hidden engineering story caught your interest, there are 4 more Mustang innovations waiting to be explored in this series.
Each one pushed the boundaries of what engineers believed possible. Subscribe and hit the notification bell to make sure you don't miss how North American Aviation accomplished what many thought impossible, designing, building, and flying a revolutionary fighter in just 102 days. That tale involves night shifts, British intelligence officers, and a cooling system that shouldn't have worked at all. Drop a comment. Do you think the Mustang's radiator truly produced thrust or merely erased cooling drag? Even now, nearly 80 years later, the debate continues. Thanks for diving deep into the world of military engineering with us. Remember, sometimes the most powerful solutions are the ones hiding in plain sight, waiting for someone bold enough to put the theory into practice. See you in the next episode.